So here is now an important aspect of these chemical reactions that you have. Okay, it's called carbonate buffering. So CO2 enters the ocean and it forms carbonic acid and bicarbonate ions and also associated dissolved CO2. Okay, because of that chemical reactions, it implies that the resulting increase in seawater CO2 concentration is smaller than the actual amount of CO2 entering the seawater. All right, this is what we call buffering. It's quantitatively the most important oceanic process contributing to the oceans as a carbon sink, and it maintains the slightly basic pH of seawater within relatively narrow limits despite the uptake of atmospheric CO2. That's what we call carbonate buffering. So CO2 entering the ocean, and some of that is packed away as bicarbonate ions, forming skeletons and shells and whatnot. And because of that, the oceans stay on their whole undersaturated, can take up more CO2. And that's also how that big number in terms of the carbon's storage capacity in the oceans, why that is so big, the storage capacity. And in the end, because you also learned about the ecological cycles in the ocean, because the detritus, the dead organic matter sinks down, only a small amount ends up on the seafloor, and this is essentially the carbon material, it's carbon, but over time it accumulates. Right? Okay, so without carbonate buffering, without this process, the atmospheric greenhouse effect would be way worse. So the oceans actually play a good role in the sense of removing CO2 from the atmosphere. Okay, I want to tell you a little bit more about this. So let's have a look at the distributions of CO2 in the oceans.